Hi everyone, I'm Yichen Tian, and thank you for attending my midterm project presentation. The title of my work is Actionable Insights from FDA Text Data for Healthcare Decision-Making. This project focuses on using advanced natural language processing, information retrieval, and clinical reasoning techniques to automatically answer a critical question. When a patient experiences symptoms, should we discontinue the drug? The FDA FAERS database is a massive resource containing over 18 million adverse drug event reports across several decades. Today, signal detection in pharmacovigilance still relies heavily on manual review, which is slow, costly, and often delayed. Therefore, the goal of this project is to automate early signal detection by answering one central question. Should this medication be discontinued given a specific set of symptoms? To achieve this, I designed a layered framework that integrates BERT for encoding case narratives, RAG for retrieving similar precedent cases, and LLM-based reasoning by long chain to generate human-readable clinical recommendations. This project uses adverse event data from FDA FAERS bulk files, covering the years from 2015 through 2024. The initial dataset was about 43 GB in size and included millions of reports. To ensure consistency, we filtered only those reports involving prednisolone, including all of its salts, extended release formulations, and fixed dose combinations with other active ingredients. Standardization and deduplication were performed using Rx norm mapping. The key fields we retained were PT, preferred term for symptoms, NDPT, indication, drug name clean, normalized drug name, age, sex, and the child field indicating the challenge outcome. For labeling, we define the challenge flag as follows. A value of Y means the drug was stopped and symptoms improved. This is a positive class and label is 1. N means no the challenge or symptoms did not improve. This is negative class and label is 0. About 89% of cases fell into the positive class. After filtering for prednisolone-related reports, we retained approximately 360,000 cases. From this, we stratified a 10,000 sample subset that preserves the original 8-to-1 positive to negative class imbalance, split into training, validation, and test sets using a 70-15-15 ratio. The data pipeline included 4 main steps. We filtered valid record with the challenge values of Y or N and sampled 10,000 cases. Each case was converted into a unified text format. Symptoms, indications, drug, age, and sex. A stratified split was performed to create the train validation test sets. We loaded the train and validation cases, about 8,500 in total, into a Haystack vector database to support RAG-based similarity retrieval. Our model lineup includes several layers of enhancements. The baseline is a BERT-based model trained on our binary classification task. We experimented with domain-specific variants such as BioBERT, ClinicalBERT, and ScienceBERT, all pre-trained on biomedical literature. And RAG-enhanced models use BERT in combination with retrieval scores from similar precedent cases. And LLM-enhanced models combine BERT with long-chain prompts for clinical reasoning. And the hybrid model stacks BERT, RAG, and long-chain together. And finally, the supermodel family uses either static or dynamic fusion mechanisms, including MCP, for multi-chain reasoning. This diagram shows how different components work together in the hybrid model. RAG retrieves similar patient cases from the FAIRS vector database, providing a score that represents historical evidence. Long-chain prompts are applied to contextualize the BERT output and generate a human-readable explanation. These outputs are then integrated and passed forward for fusion and final decision-making. In the static fusion supermodel, we apply fixed weights of 0.25 to each component: BERT, RAG, long-chain, and MCP. These weights were tuned on the validation set. In contrast, the dynamic fusion model uses a 3-layer neural network to dynamically learn weights for each component based on the prediction logics, confidence levels, and intercomponent agreement. A confident gating mechanism is applied to suppress unreliable predictions. I trained all models on a single NVIDIA RTX 4070 Ti with 16 GB of VRAM. To optimize performance and memory usage, I used FP16 mixed precision and gradient checkpointing. Dynamically adjusted batch size based on available memory, and applied early stopping and linear warm-up scheduling for BERT, and fine-tuning FusionNet with Atom Optimizer at a learner rate of 1e-3. Due to the heavy classes imbalance, both accuracy and F1 score plateau around 0.886 and 0.94 respectively. However, the ROC-AUC value, more suitable for imbalanced settings, was significantly improved. The dynamic supermodel achieved a ROC-AUC of 0.833, which is a 35% gain over the BERT baseline. All enhanced models suppressed the baseline in both performance and explainability. These slides show the interactive dashboard I developed for model evaluation. We can see different models and all performances. The dynamic supermodel stands out with clear ROC-AUC improvement and balanced performance. There are 3 main reasons for improvement. RAG helps separate borderline cases by recalling relevant historical evidence. LLM reasoning applies medical heuristics, which helps calibrate the output probabilities more realistically. And dynamic fusion learns which component to trust on a per-case basis, leading to better overall discrimination. Let's look at a real-world example. The patient experienced nausea while taking prednisolone. The model assigned the following fusion weights: BERT 0.22, RAG 0.30, long-chain 0.20, and MCP 0.28. The final output was a decision to discontinue the drug with 0.87 confidence, which matched the ground truth. The reasoning path was transparent and clinically sound. Let's recap our model structure. Our final architecture includes 3 layers of reasoning. RAG retrieves similar cases from the FAIRS database. LongChain generates human-readable recommendations. MCP executes 3 prompt chains: risk assessment, clinical decision, and evidence integration for robustness. The dynamic fusion strategy improved ROC-AUC by 2% compared to static fusion, without hurting accuracy or speed. The confidence gate also helps suppress noisy components when necessary. To showcase the real-world potential, I built a lightweight chatbot prototype using Flask and vanilla JavaScript. User can enter natural language queries, which are passed to the dynamic supermodel on the backend. The model returns not only a decision, but also relevant retrieved evidence and clinical reasoning in plain language. The screenshot shows what the user sees: a list of similar precedent cases from RAG, confidence scores from each component, the fusion weights used, and recommended monitoring action or next steps. This makes the model's recommendation clear, transparent, and actionable for clinicians. Also, there are still several limitations. The binary classification task is 2 cores. We plan to adopt a 5-level risk scale in the next stage. The current model does not yet handle polypharmacy, which is common in clinical practice. We lack real-time clinical feedback and continuous learning. A human-in-the-loop mechanism will be essential for deployment. Looking ahead, we have 4 key directions for the future work. Expand the chatbot beyond binary discontinuation to cover dosage adjustment, alternatives, and monitoring strategies. And deploy the prototype in clinics and hospitals to capture real user queries and feedback for model fine-tuning. And also, calibrate model probabilities using real to challenging outcomes collected from clinical partners. And apply few-shot and continual learning techniques to handle rare drugs and improve generalization. That's all of my presentation. Thank you very much for your time and attention. I'll be happy to take any questions or discuss your thoughts further. Thank you.